Thank you very much for this lovely presentation. Without further ado, let's move on to the next session. And let us remember Edmond Becquerel's contributions in the areas of phosphorescence. Handing over now to the two chairs of the session, Jean-Louis Lazari and Lawrence Peter. Hello, everyone. Can you all hear me? Yes, we can. My name is Jean-Louis Nazari. I'm a researcher at the CNRS Center in France. Right now, I'm in my living room. I'm a trained solid-state physicist. I specialize in semiconducting thin films. I use a technique such as heteroepitaxy and also the physical properties of thin film for electronic applications. I started working on laser diodes and also infrared photodetectors, and more recently, I've taken an interest in intermediary band solar cells. 3-5 semiconductors in particular. I have the pleasure of chairing this session on phosphorescence and photoluminescence. Thank you very much. Jean-Louis, good morning, everyone. My name is Henry Peter. I'm a professor emeritus in Bath in the UK. For nearly 50 years, I've been working on photoelectrical chemistry, and I have the great pleasure of introducing Guilhem Gallot, the next speaker. He is the head of research at CNRS and also the Polytechnic School in Palaiseau, where he is also a teacher. Guilhem is well known for his work on spectroscopy, femtosecond spectroscopy in particular. Last year, Guilhem supervised a group of 5 Polytechnic students on the plan was to restore a Becquerel phosphoroscope. There's an example of phosphoroscope that belongs to the Polytechnic School. I'd like to attract your attention to this quick video, which I put together on the building of a phosphoroscope. We made it at the Institute, and I've worked at this institute for many years. Thank you very much. I'd like to talk to you about Edmond Becquerel's phosphoroscope. More specifically, this is a collective project that we organized with Polytechnic school students, actually, last year. I work as part of the optics and bioscience laboratory, and I was involved in this project where I supervised the students. Now, the phosphoroscope, the whole issue has to do with phosphorescence. What is phosphorescence? Well, phosphorescence is part of a bigger family, the luminescence family. And I'm referring to spontaneous emission of light using different energy means, quote unquote, as opposed to incandescence. Incandescence is the production of light by heating the material. So we're talking about cold light because the material is not being heated. There are many different examples. It all depends on how you activate production of light. Here's a very well-known example. LEDs, light-emitting diodes. So the light is produced by an electric field. However, I apologize for this technical glitch, says the speaker. I'm not seeing the slide that is being displayed. Well, I'm seeing it. Interesting. Something weird with my PowerPoint presentation. Anyway, so light-emitting diodes. Glowworms is an example of bioluminescence. And then what are we interested in today? Anything pertaining to photoluminescence, which includes fluorescence and phosphorescence. So, photoluminescence is the production of light by absorption of another light. So, what's the difference between fluorescence and phosphorescence? Well, we used to call it phosphorescence from phosphorus. We have a quote from 1789, and that's the property of giving off light without combustion. So that's an old definition for phosphorescence. The name fluorescence was given later by Stokes in 1852. So the main difference between the two has to do with the lifetime, the, the duration of the storage of energy, because time elapses between storage of energy and re-emission of energy. So you have time divided by tau, and energy decreases over time based on this characteristic time. So the difference between fluorescence and phosphorescence is mostly this. So for fluorescence, it's a short time, lower than 1 millisecond, sometimes as low as 1 nanosecond. But for phosphorescence, we're talking longer durations, over 1 millisecond, sometimes 1 minute, sometimes hours. And the difference is physical as well as human related. In actual fact, it is impossible to observe these characteristic times for fluorescence to the naked eye without an actual instrument. So if we want to go further, obviously, we need to move into the world of quantum mechanics. And that's something that Edmond Becquerel knew nothing about, but we have modern scientific explanations. If we go back to this specific metaphor of the foosball, and Daniel Lanco loves his foosball, the electrons, which have discrete states here, represented through discrete states, can change energy levels by absorbing photons. Through absorption, the electron is excited into a higher state of energy. Then this introduced the S spin state. So S equals 0. It's a singulate. And this is going well because the fundamental state has a level of 0. And according to quantum mechanics, the potential transitions are done while maintaining this number. So once the electron is excited into a higher energy state, it will release its energy, possibly by emitting a photon, and that's called fluorescence. And because the transition is mechanically possible, the release of energy, that is the emission of the photon, is done quickly, and we're talking about fluorescence. However, there are molecules in which the electron can switch to an S equals 1 state, so a triplet state, and so the electron should stay stuck forever. There are other mechanisms, as it happens, that allow for the transfer of energy toward the fundamental state. And when you have states that are stored for much longer, we talk of phosphorescence as opposed to fluorescence. Let's quickly look at the history behind the Becquerel's phosphoroscope. When Becquerel made that discovery and started working on phosphorescence, obviously he built on the past 30 years. And here are a couple of important examples of the work done over the past 30 years. Now, we discussed some of them earlier this morning. In 1821, Fraunhofer started looking at the emission spectrum of certain materials, and he found what was later termed Fraunhofer's lines. And so this work was also driven by the discovery of photography in 1827 and the following years. As a result, emission spectra were collected by museums as a basis for their work. In 1852, Stokes observed that the absorption spectrum, in other words, the different colors absorbed by the materials, was different than the colors re-emitted by the very same materials. And this effect was quantified by Stokes. So there was a delay, a shift between the emission maximum levels. And Stokes called it fluorescence. There's an analogy with opalescence, as in opals, but he used the term fluoride, and fluoride gave its names to the term fluorescence. So this brings us to 1857 with the creation by Becquerel of the phosphoroscope. And this is a photo of the phosphoroscope at our school. And this is the first mechanical instrument making it possible to study the lifetime of these phosphorescent states with a resolution that is much less than 1 millisecond. There are different types of phosphoroscopes, and you find them in different collections in Harvard, in Aberdeen, at CNAM. This is the Harvard one. It's a portable phosphorescope. And I think it must have been pretty tricky to handle. But this is a more miniature version of the larger phosphorescope that you can see in the lower left-hand corner. Now, what's the underlying principle behind the phosphoroscope's operation? Obviously, no invention is based on nothing. You don't pull it out of your hat. There are two prior examples of similar machines that were probably helpful to Becquerel when he designed his own phosphoroscope. So 1834, Charles Wheatstone developed a rotating mirror to measure the velocity of electricity transmission. And this mirror was taken up by Hippolyte Fizeau 15 years later. So he modified the mirror. So he used a rotating wheel. And this is a close view of the multiple teeth, the serrated edge of this wheel. And when you rotate the wheel very quickly, you measure the velocity of light. That's what Hippolyte Fizeau did in 1849. So Becquerel took up the same idea. So he used quick moving mechanics to measure phosphorescence related phenomena. So he used two rotating discs. And this is what you can see on the engraving. I can give you more details on that in a couple of minutes. So two rotating discs at a high speed. So he used a crank and a series of cogs and wheels. And so there are openings in these two wheels, but the apertures from the two wheels are not in line with each other. So a quick story. Becquerel's own son, Henry, was interested in phosphorescence, and he discovered radioactivity fortuitously a couple of years later. At the end of the 19th century. So as you can see, there's real continuity in the Becquerel family from father to son to grandson. Now, a more modern interpretation, a more modern explanation won't be available until the early 20th century with the development of quantum mechanics. And more specifically, in 1921, the Kerr effect, the electro-optic effect. This led to the manufacturing of new machines based on different mechanisms. And obviously, the resolution drops to 100 nanoseconds, and that's thanks to electric impulses. Now, what's the underlying principle of the Becquerel phosphorescope? Here it is. You have two rotating wheels, which are synchronous relative to each other. And there's a crank, and you turn them manually. So the light comes here from the left. Either it is blocked by the first disc, or it goes through, but then it is blocked by the second wheel. So the light can never escape both discs. It never makes it past the second disc, the second wheel. So Becquerel used the sun as a light source. He also used oil lamps, Carcel type oil lamps, because he needed a strong lighting for his experiments. So this is what happens. Becquerel puts a phosphorescent sample between the two wheels. So the phosphorescent material is going to store the energy and release light after a certain time, usually 1 millisecond. And this is what happens. When the disk turns quickly enough, the energy drops after excitement and is strong enough to escape. So part of the light escapes. So the quicker you turn the wheels, the higher the amount of light that escapes is. And this is how Becquerel is able to measure the characteristic phosphorescence times by measuring the rotational speed of the wheels. More specifically, you see the charge and discharge cycle of phosphorus. When the first wheel is open, the phosphorus becomes charged. Then you block the light source, the phosphorus becomes discharged until the next cycle. And in between, the exit window opens, which means that you integrate a signal. And this signal is symbolized by this whole time or temporal area here. Now here Becquerel obviously had nothing but the naked eye, but now we have other equipment, cameras, etc., to quantify that time. Now, this is the historical instrument devised by Becquerel. See the crank? You use it, and there's cogs and wheels that you use in order to turn the wheels, and this is the observation element. And the area where you put in the phosphorus sample. And then you have a base made out of wood, and inside that drawer you still have samples, and we don't know whether Becquerel used those samples or not, or whether they were used at a later stage for demonstration purposes during classes at the Polytechnic School. I have a video here. Just watch. You should be able to hear the sound that the device makes. See the entry window? And the wheel is turning faster and faster. And then you have the second wheel, which is symmetrical, which is on the other side. Okay? So we're facing the wheel directly. And as you can see, at no time do you see through both wheels. The view is always hidden. And these are the cogs and wheels that you see at the bottom, and the crank, which you turn manually. Now, here we're turning the crank very slowly. So if I move away from the instruments, see, we're turning the crank rather slowly, but you can still hear the noise that the instrument is making. Now, in order to reproduce Becquerel's experiment, it's kind of difficult to use the instrument itself because it's a work of art, it's a historical artifact, but to reproduce these rotational speeds, if we look at the publications, we realize that Becquerel reached 3,000 to 4,000 hertz. That is, he turned it 3,000 or 4,000 times per second. So I imagined a more modern system, a simpler system to reproduce the experiment. We based ourselves on off-the-shelf systems. So a commercial motor, commercially available motor that we use for chopping the light for scientific experiment purposes. So we used an LED as a light source, a blue light source to excite the phosphorus. The phosphorus was donated by Thierry Lacroix, who's a researcher at the condensed matter laboratory at Polytechnique. So we're using europium chelate, which is particularly effective for these types of experiments, and finally 3D printing. We used a 3D printing for the hood and other mechanical structures. We carried out a number of experiments looking at what was happening either with the naked eye or using a camera or amplified photodiodes, which allowed for more accurate measurements. And this is a video of the device while in operation. See that this is the blue light source and the phosphorus, which is excited by the light, and the detection system that can quantify the measurements. Now, this is the experiment as Becquerel must have or could have carried out back in the day. So we placed a source of light at the back. You see the phosphorescence coming through. On the side, that's parasitic light. And you can you can hide it using caches, but I remove the caches for the sake of experiment. As you increase the rotational speed, as you can see, the phosphorescence emerges and actually gets through. So we are reaching the maximum speed here. It's already pretty noisy. 1 kilohertz, that's the modulation. And now we're reducing the speed again, and gradually the phosphorescence will fade away. And we're getting close to the end. So this is a cycle whereby the speed ramps up and then falls back down. Now we're fine tuning the detection system. You have the control electronics that gives you the rotational speed. So a couple dozens of hertz, and you gradually increase it. And meanwhile, you look at the signal from the photodiode. Our starting point was 80 millivolt. And as you can see, the signal gradually increases until it gets to maybe 200, 220 millivolt at a maximum modulation frequency. The interpreter can barely hear the streamish noise. Now, Becquerel used rotational speeds to achieve 3,000, 4,000 hertz. But this device only gets to 1,000 hertz. We could do better, but again, this is off-the-shelf equipment. This gives you some idea of how good Becquerel's instruments were back in the day, that he's able to do better than we can now. Now, the modulation frequency. We are able to record the signal for each frequency. And this gives us a graphic curve that matches the growth in the outgoing signal from the phosphoroscope as speed increases. So we're able to build this into a model. We turn the graph into a model using this equation. There are two important parameters. First, the modulation frequency, and then tau, the characteristic time for the energy degrowth. And then we look at the value of tau. This is the blue curve that you see on the graph. So we have a very good result, and this gives us tau. So the relaxation time is about 0.3 milliseconds. Obviously, that's something that Becquerel could not have done. He didn't have measuring instruments that were that accurate. But this would also involve a number of hypotheses that are based on quantum mechanics. And also, Becquerel wasn't a big believer in mathematics. He was a very effective and efficient experimenter, but he believed in applied physics, not theoretical physics. And the photophorescope does not achieve the modulation. As like I said, this reenactment does not achieve the same results that Becquerel did back in the day. That's how good his instruments were. So a couple of modern applications. Now, this whole concept of rotating wheels or rotating mirrors, this was used until the 1960s in off-the-shelf spectrophotometers. Those were available in the 1960s. And then in terms of fluorescence, there were lots of consumer applications such as LEDs. And in detergents in particular, there are optical brighteners, so as to make your sheet look whiter than white. So optical brightness convert part of the light from the invisible to the visible spectrum, and to make your laundry look whiter and cleaner. So also in the area of research, fluorescence is an idea that's used in biology in particular for imaging purposes. Autofluorescence of certain molecules is used in biological systems. We can also use external probes. This is an image obtained by one of our colleagues in her lab. So green means second harmonic imaging, and red means different kinds of tissue, which are autofluorescent. And this is how we're able to study the tissues. And this is high quality imaging but the resolution depends on the nature of the tissues. And there are other techniques as well measuring the fluorescence time, a bit like what I said before. And this parameter will be used as a characteristic marker of tissues. But obviously, this is highly technical. I'm not going to go into that. Now, phosphorescence. I would say that there are fewer direct applications. I'm thinking, obviously, of quartz, Casio, glow-in-the-dark watches. Here's another example. Biological imaging probes use long lifetime phosphorescence sources. They use it for imaging purposes. Thierry Gacoin and other colleagues from the lab are developing these systems. And by way of conclusion, of course, I'd like to extend my warmest thanks to Polytechnique and to the class of 2018 who were involved in my project. Many thanks to Thierry Gacoin for providing the phosphorus. And also many thanks to the team, to the musics team at Polytechnique School. Many thanks for your attention. Thank you very much, Guilhem Gallot, for this excellent, fascinating presentation on Edmond Becquerel's phosphoroscope. It was so interesting to actually see it work. I have a quick question. The Carcel oil lamp, did it work? Well, it's an oil lamp. But it's a highly complex oil lamp. There's a regulation system. The oil flow rate can be regulated so as to ensure consistent brightness. To ensure perfect stability of the light source. I understand. So these lamps were used only by scientists. They were very expensive to make. And so these are works of art today. You can find a few of them available on the market, but they are very rare and valuable artifacts. We have a question from Mohammed Sharif. The two rotating discs are connected to each other, but do they turn relative to each other? I think it's going to be an easy answer. You're absolutely right. This is exactly it. Now, getting back to this picture, see the two wheels, the blue one and the green one. Yes, they turn at the same time. They are connected to each other. But there's never an alignment between the two apertures. No other questions. Once again, many thanks to Guilhem Gallot for his fascinating talk. Thank you for listening. Okay. Taking back the microphone, thank you.